a topic that I've never heard anybody speak about anywhere, and I've never spoken about it either. So we're in for an adventure. I'm busy creating a resource. I call it the Encyclopedia of Concurrency. And what I want, my plan is the following. This is a crazy idea, but what I want to do is to create a teardown of the entire java.util.concurrent package, all the classes inside there. And of course, java.util.concurrent this has some marvelous utilities that are used all over the place to build systems which are able to be thread safe. And all of this, of course, is also built so that we can use it with Project Loom, so you can have millions of threads all working at the same, appearing to run at the same time, without having to have the debug hell we can get with other systems. So because you're all panelists, and I think we're very quickly trying to, anybody who arrives becomes a panelist immediately, you're welcome to simply unmute yourself and ask a question. It's a lot more fun for you to ask questions, and of course also for me if you ask questions. Now, we mentioned this little voucher. It's easy enough, tinyurl.com/AQS2021, caps AQS. But that voucher expires at 8 o'clock this evening. Once you redeem it, it doesn't expire. So the course doesn't expire, just the voucher expires. If you get it within the next 40 minutes, 45 minutes, 52 minutes, you'll get it. Otherwise, if you speak to me afterwards and say, oh, gee, I wasn't listening, then I'll say, oh, I'm really sorry. Next time, pay attention. All right. Now, I wanted to look at this class called the AbstractQueuedSynchronizer. And this is like the cornerstone of the entire, well, not the entire, most of the java.util.concurrent system. So I want to show you some classes that extend that. And the way that I'll do it is to just jump into IntelliJ, type AQS, which gives me to the AbstractQueuedSynchronizer, there it is, and we'll have a look at this code together. So if you have any questions, please don't hesitate to ask. Simply, unmute yourself and speak, and I'll hopefully hear you. And don't worry about your English. If it's not as good as your Polish, well, I can promise you that your English is a lot better than my Polish. So don't hesitate to ask. All right. You can also type in the question into the chat and somebody will read it to me. All right. So the AbstractQueuedSynchronizer, I said, this is sort of the foundation. This is the cornerstone that's holding everything together within the java.util.concurrent library. And this extends an ownable synchronizer, which allows you to also say who has this synchronizer. Now, a synchronizer is something which is used in order to coordinate state in some way. And the ownable synchronizer means some thread can be the exclusive owner of this thing. So for example, you might have a lock and you want to have somebody that has an exclusive ownership of that lock. So no one else can have that lock at the same time, and you can find out who that owner is. We call these ownable or owned locks. So they have an owner. All right. Now I want to take a step back before we go into this. In the past, like in the very first versions of Java, we had synchronized. And synchronized was used to mark a method or portion of the method as having exclusive access to one thread at a time, to synchronize access to that piece of code in order to write thread-safe code. But synchronized has quite a few issues. It has some benefits, but it also has some issues. And so what they did for Java 5 was they extended this, they changed it, and they wrote these ownable synchronizers where the main class that we already saw is this AbstractQueuedSynchronizer. Now, just by the way, there's also an AbstractQueued long synchronizer, which instead of having a state of an int, of a 32-bit int, has a 64-bit int. Besides that, it's virtually identical to this one. I think it's completely identical except for long versus int. So we're not going to bother with even looking at the AbstractQueued long or a long queued synchronize one of those two. We're just going to look at this one. And so what we'll do is we'll have a look at where is this used. So find usages. In fact, let's rather do it this way. We'll click on this little button here, and that shows us where it's actually in use. And you can see there's the countdown latch uses it. Semaphore uses it. You can see there's a non-fair sync and a fair sync. We'll explain in a moment what that's all about. You can see it in Reentrant Lock, Reentrant Read-Write Lock, and worker and thread pool executor. Now, let's look at a few of these. So you can see here that the AbstractQueuedSynchronizer is extended. Of course, it's abstract. So the concrete class is called sync. And this is a private static final class. Now it's private static final class. So it's private so that nobody from the outside can see it. It's static, which means that the sync doesn't have a reference to the outer object. And the way that you write Java code is you can have nested classes inside other classes. And this is one example of that. And then you've got final, which sort of seems a bit redundant because, well, it's private anyway. And if you haven't subclassed it already, well, then why do you need final? So the final is a little bit redundant, but it's quite common that the classes are final. All right, so private static final. And then I'll explain how this all works a little bit more in detail a bit later. But let's have a look at some other ones. Let's look at the, what's the next one? Let's peep at the semaphore. Now there's a fair sync and a non-fair sync. We'll look at the non-fair sync. The non-fair sync extends sync. Sync is an abstract static class, not private this time. Abstract static class. And then the non-fair sync is a static final class. Again, it's final and it's static, but it's a nested class, which means it's a class inside another class, and it's static and doesn't have a pointer to the outside object, and it's final. So just some of the technical things here. And you've got the fair sync is the same. It's also static final class. Again, doesn't have a pointer to the outside object, and that's all that it's got inside here. All right. Now you can actually see that it's serializable. I won't go into the details of that. That's got nothing to do with synchronization. That's got to do with being able to write it into a Java object stream. But it's just for backwards compatibility that they once had that, so they've got to keep it. All right, let's go back to the next. Let's look at the next one. And here you can see the Reentrant Lock. Again, it's a static final class. All right, same as before. You'll find the same with the Reentrant Read-Write Lock. Again, it's a static final class. And somewhat different is the worker and thread pool executor. So it's actually also an AbstractQueuedSynchronizer, but this time it's not static. So it's final, it's private, but it's not static. All right, so remember all of these things. It's going to be important later on. You'll be asked a quiz about that. Right? So if you weren't paying attention, saying, I don't need to know any of this stuff, well, too bad. Go look it up again quickly. All right, let's go back to my outline here. So these are the sort of the 5 that are given to you as part of the JDK. But let's also have a look at how these are used, because AbstractQueuedSynchronizer is used to build these, but then these are used to build a bunch of other things. That's what I'm saying is once you know that, you understand everything else that's following after that. So I want to look at this pending future first of all. So this is now pending future. And you can see here's a countdown latch. So if you click on that, and if you're beginning with Java, it's always good to know how to find information about what you're looking for. And to me, one of the most useful things is just to hold the command button down and click on something, and it takes you straight to where it's supposed to be used. So here, for example, if I look at latch, command B, or just clicking on it, command click, you can see that over here they make a counter latch of size 1. So what's a counter latch? Well, a counter latch would be like, let's say, for example, you need 3 resources that you need to start up. So you start your program, and each time that one of the resources is started, the database, your network server, and something else, each time that one of those resources starts, you're going to do countdown on the latch. Anybody who wants to use the system will have to wait until that has reached 0. And so here they're just using a counter latch of 1. So it's really just like a gate, open or close gate. You don't need a counter latch for this. They could have done this differently as well. They could have just have a Boolean and then synchronized. But what's nice about these concurrency classes, they give you a lot of additional functionality in addition to what you, in addition to just the counting as well. But this is one example where it's being used. And you can see that latch would then be called, they're created with 1, that's called latch countdown. Once the result has been set, they set the countdown, or if there's a failure, they set the countdown as well to say something has arrived. And then at some point you'll have latch dot await over here, which somebody calls get. Then they're simply going to wait until the latch has reached 0 before returning. So the first time we call get, it will take a while, but after that, once you've called get, it'll be very, very quick. Immediately come back immediately. So that's the idea. That's how they use it. And so this pending future indirectly uses this AbstractQueuedSynchronizer. It's very, very prevalent everywhere. Let's go back to the next one, and that is the Semaphore. So the Semaphore is your bouncer. You know, you want to go into a nightclub. You remember nightclubs? You used to be able to go to a nightclub and dance the night away. My son is a musician, and at the moment it's rather sad. They can practice, but that's about it. No more gigs. But you've got the bouncer outside allowing a certain number of threads or resources to come in at once, people to come in at once into the club. And that's how the Semaphore works. You walk in and the bouncer is counting how many people are coming in to stop having too many people in, or unless they're very beautiful, they can come in as well. But that's a different type of Semaphore. So if you go to this created font tracker, for example, here they make a Semaphore of size 5. Okay, so this is going to allow 5 concurrent font creations. That's what I think is going on here. I don't actually know what's going on, but I'm assuming that's what's going on here. So they're lazily creating a Semaphore, adding it to the app context, right? Putting it in there, and the Semaphore is going to be 5, also comma true, and the true over here means it's going to be fair. Fair meaning, because it's a Semaphore, it's going to issue the permits in the order in which people have asked for the permits. So it's going to be, you know, first in, first out for the granting of the permits. I'll talk more about fairness in a moment, but the true over here means it's fair. Fairness is highly overrated when it comes to concurrency, and something you generally want to avoid. I'll talk about that just now as well, some more. All right, so if we go back to, where it's used as well, the Semaphore is used here, for example, get, you can say try acquire. They're trying to acquire for 120 seconds. So for 2 minutes, they're going to try and get the Semaphore. And here they're trying to create fonts. So the acquire permit, for example, this is being used by the font class itself. So they're going to say, try and get the permit. They only want to do 5 at a time, so we don't overload the system and get some other weird error and exception. So acquiring the permit, once you got it, then you exit from there. And then once you're done with it, you release the permit again. So you always need to have this inside a try finally. You can see here there's a try. We acquire the permit, and then you say, finally, if we did acquire it, then we're going to also release the permit. So it's, if you've managed, then you're also going to release it. If you make a mistake here, then you're going to swallow the permits and not have very many permits left. You won't be able to have 5 fonts at a time. You're going to be at 4, 3, or 2, or none at a time being created. So that's, again, I don't actually know this code. I don't know how this code works, the font. I've done some work using fonts, but I'm just showing you how it works. All right. And then the Reentrant Lock, this one is in place of Synchronized, where Synchronized wouldn't give you the options that you actually want. So for example, array blocking queue. Now this one is actually surprisingly complex. Oh, that's the wrong one. That's my class. Let me try this one. There you go. This is surprisingly complex, array blocking queue. And the idea with array blocking queue is you've got an array-based queue. You can put elements in and take them out. It's not a very efficient queue. The array part is okay, but there's only a single lock to control putting and taking and any change that gets made to this array blocking queue. So that part's not that great. There's a whole bunch of other things which are also not that great about the array blocking queue. There's another class called the array deck, double-ended queue, which is a bit simpler than the way they do the actual double-ended queue business, or at least the circular arrayless structure. So that's a bit simpler the way they've done it, but array deck is not thread safe, whereas this is thread safe. So with the Reentrant Lock, this now uses internally this AbstractQueuedSynchronizer. So and that gives you a slightly richer interface to be able to, for example, have timed puts, like offer something for some time to the array blocking queue. If there's no space, then it simply times out and returns false if you can't offer it within a certain amount of time. Or if you want to get something from the queue and the queue is empty, you can say, try for 1 second. If you don't get anything, then give back null. So these are the ways that you can use this queue. And all of this is actually implemented using this Reentrant Lock. So what you do is you'd wait, you'd try and wait for a certain amount of time for example, not empty. So if you look at not empty, you'll see that's being waited on. Here, when you say poll, I'm waiting for a certain amount of time, and if I get the answer within that time, then I get back the object. Otherwise, I simply return null. And this simply uses a method called wait nanos, which is defined inside the condition class, and that, of course, comes from the AbstractQueuedSynchronizer. Everything goes back to AbstractQueuedSynchronizer. So, all right. The other one is the Nio Socket Impul. And there's some interesting code inside here because they actually have 2 different locks. They've got a read lock and a write lock. Now, a lot of people, when they see that, they say, oh, right, it's a read-write lock. No, it's 1 lock for reading and 1 for writing. And the reading means we're reading from a socket, and the writing means we're writing to a socket. Both of these have to happen in a thread-safe way, because if you have 2 threads reading at the same time, they'll read each other's data. And same with writing, 2 threads writing at the same time is again going to cause issues there. You're going to overwrite each other's information. So, so even though you have a read lock and a write lock, these are both exclusive locks. And I'll talk about that whole concept in a bit as well. What that means to have a shared lock and an exclusive lock and a non-exclusive lock. If you have any questions, please ask away. I'll be very, very happy to get your questions. Otherwise, I'm assuming this is all far, far too easy for you, and I'll make it a bit more difficult if you don't ask questions. All right. So then we've got the cyclic barrier. That's another one, which is in a way similar to the countdown latch, except that it goes in a cycle. It's a lot more complex than the countdown latch. And again, they've got a reentrant lock inside and a condition. So this one doesn't directly use the AbstractQueuedSynchronizer, but it uses it indirectly. So there's a lot of the code that's inside the java.util.concurrent uses this AbstractQueuedSynchronizer. All right, reentrant read-write lock is also one that's used. And here you've got, for example, the managed bean repository that uses this. And for example, if you're doing let's try and find it here. There's the lock, right? Look at the lock. Come on. If you're doing a get, a read, you're first going to get a read lock, then lock it, and then finally you're going to unlock the read lock. So this is what we call a shared lock or a non-exclusive lock. And then we also have another place where you'll find it being a write lock, which is anytime that you're changing something. For example, you're trying to add something here, I think. So this is the add mbean, and add mbean is going to create a write lock dot lock, and then finally do a write lock dot unlock again at the end to unlock it again. So there's just some examples of where these things are being used. So how it's typically used. So the AbstractQueuedSynchronizer is most of the time used indirectly. Most of the time, you're not going to use it directly. You're going to use something which uses this AbstractQueuedSynchronizer. So most of the time, you'll use, for example, a linked blocking queue. And the linked blocking queue uses the reentrant lock. And the reentrant lock uses the AbstractQueuedSynchronizer. So most of the time, it's not direct. But if you do want to use it directly, you typically would have it as a static nested class. Most of them are static final nested classes. They can also be private. At the very least, it should be non-public. So I'll make it non-public because it's probably the most, in fact, even the final is not absolutely necessary, but most of the time they're final as well. So it's most of the time static final, non-public nested class. So you wouldn't have a class that is actually it is actually AbstractQueuedSynchronizer. And the reason why is that AbstractQueuedSynchronizer actually has a lot of methods that people could call, and it would be very confusing to use. We have, for quite a few different ones, we've got fair and non-fair options. Fair means that that if somebody else has been waiting longer, that you let them go first. So every time you want to get the lock, you have to see, is there anybody else? Am I the one? Am I the lucky chosen one? Or is there somebody else who was there before me who's been waiting longer than me, in which case I'm going to let them get the lock. So that fairness means we have to have a queue of who's before me, and every time that I ask for it, I'm going to see, do I actually, will I give this or not? The non-fair is the default, and with the non-fair, it's not unfair, it's just that we don't lock. It's like if you say, well, here, I want to call the lock, I'm just going to try and get it. And if I'm the lucky one and I get it, that's great. I'm going to move on. I'm not going to cry over somebody else who might have waited longer than me. I don't care. If you waited longer, that's too bad. I'm going to get it anyway. And the fair seems like a good idea. I remember when I was a student, I thought it would be a very good idea for everybody to have, sort of equal amounts of money. Until I started earning my own money. And I realized maybe I should change my mindset a bit. Maybe that's not the way I want to be forever, because, I mean, life as a student is so much fun, right? I mean, I spent my days playing snooker instead of going to classes. I still managed to somehow get my PhD in computer science. Don't know how, but yeah, I spent 3 years of my degree playing snooker. And I wasn't even good at snooker then. That's the problem. If I was at least good at snooker, then at least I would have said, well, I didn't waste my time. But I played snooker and I didn't become good at snooker. So that's like a really, really dumb thing to do. All right. So even though non-fair seems like it should be unfair, it's not actually unfair. It's not unfair, it's non-fair. That's a very different thing. Fair means I go strictly according to order of who asked when. Non-fair says, I don't care. If somebody gets it before somebody else, that's tough. Too bad. We'll try again next time. Unfair always gives it to one. It's like the favorite thread, the favorite child always gets a one. And quite a few of the classes, I don't know if you noticed it, actually have fair and unfair options. Or sorry, I just said it myself. Fair and non-fair options. For example, if you look at the Semaphore, we've got here the sync, first of all. The sync is AbstractQueuedSynchronizer. And we'll get into the details here. They've got a non-fair try-acquire shared. We have to get the state. The state is an int. It's just a 32-bit int. And it works out what the remaining is available minus acquires. If the remaining is less than 0, then I'm not going to even try. Otherwise, I'm going to do compare and set state. And compare and set state is a method which does a compare and set. Compare and set is tries to write it, but it only writes it if it finds the expected state in a variable. This is a very important construct we use for keeping things correct. So when you say compare and set state, we're passing in this, by the way, is class called unsafe, which we would never use in our own code. The reason they use it here is because of bootstrapping. They don't actually know in which order class will be loaded. And so they actually want to make sure that this is loaded before they start. And so they use unsafe. Normally you'd use something called a var handle, but that's not so important now. So compare and set int of this object, the state is sort of the offset into the object. That's a sort of point arithmetic into the memory of the object, and then we're expecting it to be the current value, and we're trying to change it to the update value. And if we find that it is the expected value, then we change it. Otherwise, we do this whole operation again. So this is like an infinite loop here, but it's not really infinite because at some point we're going to manage to update this. If there's no contention, if there's only one thread trying to acquire this this at once, then compare and set state will succeed very quickly, and you'll be out of there within a few microseconds or maybe hundreds of nanoseconds. But if you have multiple threads trying at the same time, then they'll overwrite each other's work, and you'll simply have to try again until you succeed. So there's no concept of order, in which order things must happen. So that's sort of the method that was written inside Sync. I actually don't like this design at all, but I didn't write the code, so I can't really comment on that, because inside the non-fair sync, they simply say inside try acquire shared, they call non-fair try acquire shared. And then inside try acquire shared of the fair sync, it's almost exactly the same, except that they say, do we have anybody else ahead of us in the line? If yes, then return -1, which means we couldn't get this. All right. So any negative number means we weren't able to actually do it. And so you can see that there's not much difference between fair and non-fair, except fair checks whether somebody else was ahead of me in the queue. And if I do this, I'm going to get a strict FIFO order. And we saw this actually in the font. For some reason, they wanted to make sure that they load or acquire the fonts in the correct FIFO order. And so they do it like this. If they didn't have that, it would just be randomly whoever, getting the fonts, and they wouldn't come out in the FIFO order. So that's fairness and non-fairness. You can see this in the Semaphore. You can see it in the Reentrant Lock and in the Reentrant Read-Write Lock. They can all be made fair. And then, of course, you can also make the abstract blocking queue fair, which will then simply make a fair Reentrant Lock. But fairness is overrated. If you have fairness, you typically will get much worse performance, right? So I'm going to try something. I actually have never tried this before. So it's going to be a fair Semaphore demo. Semaphore demo. So I don't know what's going to happen. I really haven't got a clue because I've never done this before. This particular experiment. We're going to make a semaphore. We call it the bouncer. Equals a semaphore. Let's give it of size 3. Right? And then I'm going to say, and this is going to be I'm going to say test bouncer. Right? So test method needs to write, of course. And this is going to take a bouncer. I'm going to say int stream.range from 0 to, let's make it 10 million to start with. It might take too long, but maybe not. And we're going to say dot parallel. So we're going to have 16 threads on my machine. I've got 8 cores. So it's 8 cores, 16 hardware threads. Dot for each, we're going to do the following. For each I, we're going to say bouncer dot acquire. I'm going to say uninterrupted because I don't want to actually worry about interrupted exceptions. So I acquire uninterruptedly, and this should come inside a try actually. And then finally, I'm going to say bouncer dot release. I'm going to give back the permit again. So I'm just simply going to get the permit, and then I'm going to give it back again. All right. So I've got 16 threads at the same time. We're going to do this. Fight for these 3 semaphores. All right. And then we're going to see how long it takes to run this code. So we're going to say here, print out the bouncer. And then you'll run it, and we'll see how long it takes. Now, I've got no idea because I've never written code like this before. This particular one, 10 minutes too slow, we'll make it 1 minute. 10 minutes does seem a bit slow. It's not too bad. 2.5 seconds is not very fast, but it's also not too bad. Like we can afford to wait that. Okay, so that's the first semaphore example. And now I'm going to inline this over here. There we go. And we're going to run a second experiment. We're going to say, comma, true, which makes it fair. So it's going to be a fair bouncer. So it doesn't look at how what the thread looks like, if it's glamorous and beautiful, or if it's some ugly, fat thread like myself. It doesn't care. It simply says who was here first, and that thread gets it. So it's a fair bouncer. Let's see how fast that is. So the first one was 2.5 seconds. And we'll see if the second one is slower or faster. So 2.5 seconds. 1, 2, 3, 4. Okay, it's obviously slower, but I've got no idea how much slower. And I know that it could be really bad. So what we're going to do is we're going to stop this, because it could take, I won't say days, but it could take a while. Let's make it 1 million. right? So 1 minute instead of 10 minutes. So I would expect it to be about a quarter of a second or so, maybe half a second for the first one. It does take a while to warm up. So, okay, so it's 1, 2, 3. This is what you get when you have fairness, see? You're trying to force fairness. There are 16 threads, and they're like, no, I was first, I was first, no, I was first. There you go, 50 times slower. That's not bad, eh? That's quite a big difference. Let's, we'll do one more change just to make it a bit better. The test a bit better. We're going to make this to be, I'll make it 300,000. And I'm going to run this test 10 times. So 0 to 10. And there we go. So run that 0 to 10. And now you'll see it doesn't actually show which the fair one is, which the non-fair one is. But we know the fast one's an unfair and the slow one is the fair one. So now you'll see it warming up. And you can see the fair one, once it's warmed up, goes down to like 73 milliseconds. The other one's like 4.2 seconds, so 3.7 seconds and 90 milliseconds. So it's about 303.8 divided by 80. That's pretty fast. So you can see there's a big difference between the two. So what's that? 3 divided by 90. It's about 40 times faster. So having it non-fair is a lot faster. If you absolutely need to have FIFO order and fairness, well, yeah, then you do it, right? But otherwise you don't bother, because it's actually the throughput just goes down the tubes with this. And you'll find similar types of experiments, similar type of results you'll find with locks. If you take an arrow blocking queue, all of those, it's like they put in this thing called fairness, and then they realized, wait a moment, maybe fairness isn't such a good idea. Maybe we shouldn't have made it fair. So I don't even know if anybody uses fairness in the JDK. Oh, actually, we saw one. Sorry, we saw one. I take that back, because we saw somebody using fairness because they wanted to make it FIFO. But it's not a case where they're getting like 1 million fonts. Maybe they're going to get 20 or 30 fonts, not 1 million. So then it really doesn't matter if it's fair or non-fair. All right. Okay. So then, there's other things like interrupt handling. Now, the interrupt handling is interesting because if you look at so normally, if something runs for a long time, you can interrupt it and it will then exit with an interrupted exception. For example, if you've got a blocking queue and you call take on that, if you get tired of waiting, you can interrupt that thread and it will then exit with an interrupted exception. In my little example that I showed you just now, where was that example now? It was the fair Semaphore demo, this one over here. And this one, I used acquire uninterruptedly. If I make it acquire, then actually the code is wrong, because now, in fact, I actually think the code was slightly wrong to begin with. I think that this acquire interruptedly should actually be before the try. This is how I would have written it. The reason I wrote it inside was because I saw that somewhere and I just copied it. I saw it, I think in one of the examples I showed, it was actually inside, but it's actually better in front. And if I said acquire, normally you have the interrupted exception, you then have a catch interrupted exception. Oh, no, that's wrong. That should be, oh, I need to do a try catch around the whole thing. Well, what you don't want is to try and catch around the whole thing. What you don't want to do is to have the interruption mean you're also going to try and release it. Because with the Semaphore, you can release it more often than you acquire it, which means you'll end up having more permits than you actually started with. So that is quite a dangerous thing to do. So, but if you look at how it's implemented, the acquire method inside Semaphore simply says, sync.acquire shared interruptibly. And this method is a final method inside AbstractQueuedSynchronizer, which manages the interruption for us, right? Versus the other method, which is to acquire uninterruptibly. Let's go back to what we had there before. Uninterruptibly. Let's get rid of this interrupted exception. And this one calls the method acquire shared as opposed to acquire shared interruptibly. And here they basically, again, have a what we call a template method that has the algorithm for managing it without allowing interruptions, ignoring interruptions. All right. So all of that's actually managed internally by the AbstractQueuedSynchronizer. We don't have to do it on our side. All right, now I mentioned to you this template method. Now, one of the things that you absolutely need to learn, especially if you're a beginner in Java and learning Java, or in fact, anything to do with Java, object orientation, you need to learn this book, right? This has got nothing to do with Java as such. It's got to do with, oh, that's the wrong one. It's got to do with design patterns, good design. The reason I recommend this book, it's very old, maybe older than some of you, but it's a book which was very popular when Java was conceived. It was like the thing, right? Everybody was doing that. It's like that was the snapshot of when Java was around. You know? Everyone was reading that book. All the programmers were like reading this book. And so it's used throughout the JDK. All over the place, you'll see design patterns appearing in again and again. And there's another good book, which is a bit more modern, but it's also excellent, called Head First Design Patterns. Another very good one. Ignore the goofy pictures in the front. It's a great book, technically, really good book. Head First Design Patterns and Gang of Four Design Patterns by Erich Gamma et al. So these are really good books to read and to study if you're going to be a computer programmer. And especially if you want to use Java, because Java uses design patterns all over the place. So if you know the design patterns, you'll understand what's going on far better. And one of the design patterns in here is the template method. All right, so you open the thing in front and you say, behavioral pattern, page 325, and you open it there and they give you examples and they show you exactly how it all works. I've also got, of course, a very detailed course on design patterns, a 4-day course on that. But you get this whole template method showing you exactly how it works. Now, it doesn't show very well, but there you go, template method. It shows the examples and so on. You can probably get it in Polish as well if you want. I've actually got one in German because I'm teaching the course in German. I need the terminology. All right, so the template method is being used here, and the template method consists of template methods and primitive operations. And the primitive operations are going to be called by the template method. So there are 5 different primitive operations. There's try acquire, and they pass in an argument. Now, this argument might or might not be significant. For example, for the lock, for the Reentrant Lock, the try acquire is not significant. They don't use it. So if you look at it, let's look at the Reentrant Lock again. Oh, that's too many E's. Reentrant Lock. You'll see that they have the try acquire. Oh, actually, sorry, they do actually have it. They do use it. They do use it. I thought they didn't use it. Let's look at the, okay, so this uses it. Okay, so this one does use it for some reason. I'm not actually sure why, but okay, they use it. But let me try the Semaphore definitely uses it, and the countdown latch definitely does not use it. So you see the countdown latch. Oops, I didn't have to do that. No, don't do that. Oh no, what have I done? I've destroyed my lovely setup here. 1 second, please. Let me close that. Right. So that's going to be the count on latch. It's going to be, here you can see the int acquires, try acquire shared. Here, they don't use the acquires. And here you can see the int releases, they don't use that either anywhere here. So normally, if you don't use something, it's better to call it like ignored or unused or something like that, instead of calling it acquires and then you don't use it. So it just depends on the implementation. There are certain places where it's used, other places where it's not used. All right. But these primitive operations is what you'll implement. You'll say try acquire, try release, try acquire shared, try release shared, and is held exclusively. All right. So the try acquire means that only one thread is allowed to acquire that at once. So it's like an exclusive acquire. And that's, for example, if you want to get an exclusive lock that nobody else is allowed to use this piece of code at the same time. Now the thread can call that method at the same time. Then you need to use a try acquire. But if you have, for example, a countdown latch, all the threads at the same time can try and call countdown or wait at the same time. And then you want to rather use a try acquire shared and try release shared. And of course, to find out whether it's held exclusively, for example, somebody else calls try acquire, then I hold it, then is held exclusive will come back as true. And so these, all you do is implement these primitive operations, and then if you implement these, you get the full extent of all the different template methods already written for you. So for example, if you want to do an acquire, this is an acquire which doesn't throw interrupted exception, or one which does, or one which tries for a certain amount of time, one which releases, one which acquires shared interruptibly again, try with a certain amount of time, or release shared. So all of these are all ready for you, all built already. So let's have a look at, let's try and write a one-shot latch. Okay, now the one-shot latch is basically this over here. I'm going to try and do it. I don't know if I'll get it right, but there's only one way we'll figure it out, and that's to try it out. I like to live dangerously, as Adam will tell you. Somewhat of a risk taker at times. And here's my example of that. So the one-shot latch. And I'm going to do this as an abstract queued synchronizer. In fact, before I do that, this is a one-shot latch. Let me show you how to do this using Synchronized. So I'm going to do it with Synchronized first, and then I'll do it with the AbstractQueuedSynchronizer. So it's going to be synchronized. Note. So there's a synchronized, implement all these methods. And it's a one-shot latch. So it starts off as, we're going to have a private, let's say, volatile Boolean signaled equals false. Start off as false, and is signal simply returns signaled, like so. Signal will say synchronized void signal, and now we're going to say signal equals true, and anybody who wants to know about this, we're going to let them know that we've just been that we've set signal to true. In fact, we only need to do this if signaled is false. So if not is signaled, then we do these two things. If it has been signaled, we don't need to bother signaling a second time. Inside the await, this is fairly easy. We're going to say public synchronized, and we're going to say while not is signaled, we're going to simply say wait over here. We're going to keep on waiting until we have been signaled. So that part is all fairly trivial, but now it gets a bit tricky because we also want to be able to wait uninterruptedly. Let me show you how to do that. That's really a bit more complicated. It's similar to this, except we have to worry about interruptions. Oh, and by the way, also up here, we should have started by saying if thread.interrupted, throw new interruption exception. You don't need to know all the details why I'm doing this. It's just to make it correct. All right. So wait interrupted again. We now need to say Boolean interrupted equals thread.interrupted. We need to find out what is the current state. And then inside here, we need to wait and and we need to put a try catch around that. That's the wrong one. It's this one here, try catch. And if I get interrupted, I want to say interrupted. No, interrupted equals true. So it's just to notice I was interrupted. But of course, I still have to generate this interrupted exception, which is rather ugly. Have I just stopped? Oh no, I'm still working. Okay. Just wondering about something there. All right, so and then once I exit from all of this waiting, then I have to say if I was interrupted, then I need to say thread.current thread.interrupt. So it gets quite tricky to get all of this code right to make sure that everything is correct. It gets fairly complex. Let's try and do this using the AbstractQueuedSynchronizer, the absolute basics. One shot latch, AbstractQueuedSynchronizer. So we're going to, this time do it quite differently. We're going to start by saying we're going to have a private static final class sync extends AbstractQueuedSynchronizer. AbstractQueuedSynchronizer, this one. We don't need the AbstractQueued long synchronizer because we only have 1 or 0. So that's the state. The state's going to be 1 or 0. And then we're going to override the two methods. Try acquire shared and try release shared. So it's going to be shared. So as many as at once who want to can get this at the same time. So you're just going to get these two, try acquire shared and try release shared, these two. So try acquire shared is going to say, we're going to try and try acquire is when we're trying to await. That's where we're trying to acquire. And here we need to see return get state is equal to 1. If it's then, otherwise you give -1 back. I think that's how I would have done that. I actually have to check my code. Try release shared would say, by default set get state would start with 0. So here we're simply going to say set state of 1 and return true. I think that's the wrong way around. Try acquire shared, try release shared. I'll have to check my cheat code.
Cheat code? You said that you're writing this for the first time.
No, I haven't written for the first time, but I read it. This I haven't written for the first time. The other part I read for the first time.
We have a question from the audience. I don't know if Tomek wants to ask it personally, or should I read it?
Okay, I can ask it. I wonder what would happen if we removed volatile from the code. Volatile keyword. There is only one in the code.
Oh, okay. You mean with the synchronized one?
Yes.
Yeah, that wouldn't be
initial
correct
version.
anymore. I'll explain that in a second why that's not correct anymore. It's good.
Oh, okay,
good
thanks.
question. Good question. But I'm looking at the code I wrote yesterday, and it looks similar to what I did, right? If is signaled the try-acquire shared, then return 1, otherwise -1. And is signaled says get state equals 1. So the only thing I did differently was is signaled is really supposed to be this. That's supposed to be is signaled, right? And sorry, this actually should be a method. In fact, I'll keep it like it is. I'll keep it like it is. Or I can actually have the method is signaled as part of my sync. It might make it a bit easier. Let's add that in here. I think that's a good idea. We'll have this get state equals 1. There's the only thing I had different in the code I wrote the other day. And then the other part looked correct. So is signaled will simply say, and this source here should be is signaled, return is signaled, then 1 or -1. And then the is signaled would be simply saying, now what I'll also have to do is to make a sync. So the one-shot AQS will have a private final sync equals new sync, right? And then is signaled would say return sync dot is signaled, right? The signal wouldn't be synchronized anymore. Get rid of that. And signal, it would now be simply saying sync dot release shared. And the actual argument isn't used. So you can either call it ignored or unused. I'll call it unused over here, just so that if you look at it, you say, this argument's not actually used here. All right, so you say release shared 0 and await, where we throw in the exception will be sync dot acquire shared interruptibly. That's the one you want, the shared interruptibly. Again, the value doesn't matter. Let's put in 0. So it's very easy. And the other await is just await sync.acquire shared without interruptibly. So instead of all this really complicated code with the loops and having exceptions being thrown, we simplify this quite nicely down to simply an acquire shared. I think this is correct. I think I am, but I'm not 100% sure. So I wrote, obviously I wouldn't come completely unprepared to this. I do prepare for my talks. I spent quite a bit of time preparing for this talk. But I wrote this AQS latch demo where I try out different approaches. I'm going to run this just to show you. And then I'll answer that other question as well some more. I'll get back to the question about the volatile. But I want to just run it, make sure everything works. Then I'll put the other 2 that I wrote now into that list and make sure they also work. So these all work, great. Now let's do the other 2 as well. We'll put in here the, what was it again? It was the, of course, this is going to be a bit different because it's a one-shot latch, which is a, so I need to actually move this away from here. Yep, that should work. And then it should be able to say, sorry, we don't have this now. This one-shot latch AQS, I think, is the one. So it's going to be, but I've got this one here already. So I'm going to rename this one a bit, just to give it, this will be the talk demo, just to give it a different name, because I had just had the same name for both of these. So we do the talk demo as well. Talk demo. All right, then I want to include those in my test to make sure that it's actually correct, because I'm not sure That's why one has tests, right? If everything was always perfect, you wouldn't need to get paid to write code. But seeing that we're not sure, we're going to just put this in here. And the other one was the AQS. Right. Let's see whether I got it right. The reason I'm so unsure is because I actually made a big mistake when I was doing the code. I was lying yesterday on the couch coding, and I was like, wait a moment, this is wrong. It's like nothing worked. And then I fixed it. Well, like now here, for example, current thread's not owned. So there we go. That's exactly what I'm trying to say. Is oh, that's interesting. Oh, how did that happen? Oh, I forgot to synchronize the method. There you go. As I said, I wasn't sure at all that this was correct. That's why that's where I wrote the test, to make sure that to find mistakes like that. If you're a beginner, you'll see people like me fumbling around. You go, well, am I going to be like that when I'm 50? Hopefully. Hopefully you'll be like me when you're 50. Hopefully you won't be like, I don't know, manager or something. That's really boring. So it works. So the code works. Now, let's get back to the question about the volatile. Why does this have to be volatile? The reason is that I've got the method is signaled, which is public. And I want to make sure that I can get the correct state of the signals. If I didn't have that, then I could actually get a problem. Let me show you an example of that. So, oops, let's go back here. So this is going to be the one-shot latch synchronized talk demo. Okay, so I'm going to add another part to my test that's going to check that the signal is actually signaling. So it's going to be fun. Let's try this out. I don't know if I'm going to be able to write this code, but I'm going to try. It's going to be test latch supplies out for each. We're going to say test signaling. Right. So this is going to be a bit different. And what we're going to do here is we're going to have one thread which is going to be waiting for the signal, but it's going to just spin in a loop, waiting for the signal. All right. So instead of using the proper mechanism of calling acquire or await, we're just going to spin. So in fact, we're just going to make one thread. We don't need multiple threads. It's a single thread. This is going to say, while not latch.is signaled, because this spins around like crazy until it's been signaled, right? We're going to say threads.start. This should be called thread, not threads. Thread.start. And then we're going to, what next? Next, we're going to say, so thread.start, and we're going to say, now we're going to sleep for a little bit, silent sleep of 50 milliseconds, just sleep for a short bit. And then we're going to say latch.signal, right? And then we're going to expect that thread to stop pretty quickly. So we're going to say, I would expect after another 50 milliseconds that the thread should be terminated. So I'm going to make sure that I've got that over here. So it's going to be assert same, that the thread state should be terminated, right? And if it's not, I'm going to fail. All right, so this test that the test signaling is working correctly. Now, I think that 50 milliseconds might be a bit short. I'm going to make it a bit longer, 500 milliseconds, just to give it a chance to actually inline the value and to do it this way. Let's run it and see if everything passes. I would expect everything to pass now. Everything should be correct at the moment. I'm holding my thumbs, hoping it's going to work. Please work. Please work. It should all work. Yeah, come on, it's all going to work. Come on, it's going to work. Where's my confidence? Come on, it's going to work. There we go. All works. Fantastic. Now let's go back to the synchronizer talk demo, take away the volatile, and run it again. And I'll watch and be amazed. That all works. That all works. And that does not work. It's broken. It needs to be volatile, otherwise you might see old values.
And if you make a signal synchronized, would it work right now?
Yes, that also would work. Synchronized. That would work too. And it would be approximately the same speed. So you're not going to get a really big performance difference either way. But that would also work. So yeah. I'll stick with the other one. Was another question, or was there just one?
I wonder if we remove synchronized from signal method, would it be incorrect? Yes. We have volatile in the property.
Yes, it's incorrect because you have to be synchronized on the notify all.
Okay.
Okay. And if you remove, let's say you did this, synchronized, and then you put synchronized around this, okay? It would also be wrong because now you might send the notify all twice. Okay, two threads at the same time called signal. They both see that it's not signaled yet. Then they both set it to true and notify all. So the most correct is to have the whole method synchronized. Like this.
I remember that really, really long ago, volatile was kind of a thing which some people were telling that you should use it very consciously because not all JVM implementations were dealing good with this keyword. Is this still a case, or?
It used to be a case, but quite a while ago. It was before Java 5.
Okay.
Before that. That just shows how long we've been using Java 4.
Yeah.
It used to be a problem in that it wasn't well defined, but it has been well defined now. The JSR, I think 133, I think, defined precisely how it's supposed to work.
So one more question. So what is the difference if we make signal synchronized? Is signal synchronized or we add volatile? What JVM? What's the difference in JVM internally?
Well, the difference is that you don't have to synchronize. You don't have an exclusive lock. Let me show you something. Which I think will probably amaze you. Right? Well, maybe we'll see. It might take a lot to amaze you. Okay, here's a thing called a cow remove contention. That's the one. That's the one. All right. So this is now a copy and write array list. Now, if you look at the current version of copy and array list, it's got a volatile array, the copy and write array list, and it's got a lock that they use internally for the locking. Right? So by having the array volatile, they can always get the correct value, the most up-to-date value they can get without actually doing a synchronized. All right? So if you look at remove object, over here, they get the array. Then they find, is the element inside that current snapshot of my copy and write array list? If it's not, well, it's not there. We can simply return and say, well, we didn't find it. If it is there, then they look at it a second time, and now they do the synchronized. So they avoid doing the synchronized up front. They only do it once they've determined that the element actually is there. So it's like it's an optimistic read. We call it optimistic read here. They check, is it there? It is there. Now we do another one, and now it gets complicated. Now we find out, has it changed? If it has changed, okay, then there are a whole bunch of different conditions of what could possibly happen. But what I want to show you is this code. Now I'm going to run this code, Java 17. No, not this code, not this, my test. And this test here, what it does is simply, it simply goes and calls remove null from the list. Null is not in the list, so you're just going to call remove null from the list. Do it a million times, null. And I run the code, and this is now Java 17. And when you run the code, you'll see it runs 800 milliseconds. Not too bad, 800, 750 milliseconds. That's pretty good speed. Okay. If you take the same test and you run it with Java 7, so Java 8 was already fixed, but Java 8 run the same code, which was the car remove contention over here. Okay. Instead of 800 milliseconds, it's a bit slower. Okay, because here they do use Reentrant Lock, which is actually quite good. Reentrant Lock is quite good for doing for managing very high contention. But in this case, because null doesn't actually exist inside the list, there's no reason to even remove anything. There's no need to contend at all. And so in this case, it's much slower. I said 8 times slower. 8 times slower, Java 7 versus Java 17, I would imagine. So it should be about 6.5 seconds, although maybe there's a bigger difference. I sort of started writing a comment and then I stopped. It's actually worse. It's more like, what's it? It's 33 seconds divided by 800. That's actually a lot worse. 33 divided by 800. It's like 40 times slower. Java 17, well, Java 7 versus Java 17. Same code, and such a drastic difference in performance. Because here in Java 17, they're doing a volatile read, then they're doing a check, and then if they discover that they're going to need to do some work, they simply do it again, but this time with the synchronized. And so if you really want to know how that type of coding works, I'm going to have to point it to my website, javaspecialist.teachable.com. Let me type it into the chat, because they have got these teardown classes that explain precisely how one actually would write code like that. Let's put it to everybody. Send to, oh, okay, I think it goes to everybody. javaspecialist.teachable.com. And I've got these teardown classes where I spend an incredible amount of detail on each one of the different classes to see how they actually work. It's a completely crazy idea to do that, because I'll never get the money back for the amount of time I spend on these things. I spend like a couple of weeks on each course. Each course is like 4 hours. And it's like just looking at one thing. 4 hours looking at array blocking queue, and 4 hours looking at copy and write array list, which I thought would take about 10 minutes. But when you go looking at it line by line, you discover an incredible, this huge amount of information you never would have imagined. And yeah, so it ends up being, I'll never get that money back that I spent on it, but it was just so much fun. I couldn't stop myself. My wife was like, so how many of you sold? I said, don't ask, don't ask the question. They're too much fun. You learn a lot from them. I learn a lot from them. Okay, any other questions? Did we finish everything? I think we did. Yeah, I think we're basically done, unless you have questions. Some of you wanted to actually, I think you had some quizzes as well, didn't you?
Is there a book you would recommend which covers the Java concurrency issues?
No, there isn't.
No, there is.
What about the Java concurrency in practice?
No, it's too old.
Too old? Fine.
It's old. I used to recommend it, but that book was written before Java 6 was around, was properly released. And there've been too many changes. It's really a lot of changes. So there's unfortunately, it actually isn't a book. There's no book that will tell you this stuff. Brian needs to update his book, but he hasn't done it yet, so there's no book.
So maybe any other sources you can recommend about the concurrencies?
Well, you can do what I did, which is read the source code, right? And that's a good habit to get into.
Yeah, that's true.
Because the way that I figure this out is I don't just guess stuff. I actually read what's in the Java docs. I read what's in the source code. I've got a course, like a 3-day course on Java concurrency performance. I've done it at Allegro a couple of times. I've got a 4-day course, which is a longer course on concurrency. But this stuff is quite important because the whole Java infrastructure is gearing up for Project Loom, which is looking at being able to have millions of threads instead of just thousands of threads, being able to scale out like that. And the thing is with Project Loom, it's not really compatible with Synchronized, but it is compatible with AbstractQueuedSynchronizer. So if you use that, then you've actually got something which will be compatible with Project Loom. So that's something which is pretty useful. I think. We'll see.
Yeah. So my question was, what are your thoughts on reactive programming and code coroutines as opposed to like default Java thread, default Java threading? Yes.
Well, native Java threading doesn't work, right? That's very well established fact. There's so many ways to try and get around the native Java threading. It's not funny. I did a little demo where I did just a simple blocking server, and it's like a few lines of code with native threading, and with like a non-blocking server. It's like pages and pages of code. But the thing is that the blocking server is very easy, but it just blows up after a few thousand threads, right? And it just doesn't scale, right? So the problem with native threading is it doesn't work, right? It can't scale beyond just a few thousand. And if you want to have lots and lots, well, you need something different. For example, I don't know if my demo is actually active at the moment, but I've got this one demo, which I wrote with Project Loom, which is sort of, Java likes to copy stuff from other people. So the one thing that they're doing at the moment is copy this whole idea of coroutines and goroutines and all these, virtual threads, lightweight threads, you name it. That what you'll be able to do in future, hopefully with Java, is to have something which is called a virtual thread. JPS. Yeah, it's actually running. So I've got this server chatter and socket limits chatter running. And how can I show this to you now? Let's go to log. Tail minus F client. I started the server 3rd of May. I was doing another talk about some other topic, Project Loom. Yeah, it's still going. So I've got 2 million virtual threads sending messages to 2 million other virtual threads just with a direct connection. So 2 million sockets open and happily sending messages backwards and forwards, right? I'm only showing every 10,000 message because otherwise it'd be flooding it. I'm not just flooding it all the time, but it's very happily running along. I've been doing that for like quite a while. And if you go to, let me show you something here. That's the prepare for Loom. What was it? Scripts. I haven't looked at this for ages. I mean, since for 6 weeks, so I was forgotten where to find things. All right. So here you can see the histogram of what's currently running on there. You can see that they are on the server client, on the client side. This is 2 million, simulation of 2 million connections at the same time. And similarly, within one virtual machine, you've got 2 million virtual threads. So the good thing is that this is all going to be integrated with flight recorder and all of that stuff. So it's very easy to analyze mistakes, to find problems. Unfortunately, it's not production ready yet. They still have, crashes, things crash and so on. But that's where Java is going. It's going to be a similar direction to sort of Kotlin coroutines or Go routines. It's just the same type of idea, same direction, to be able to simply have sort of continuations and stop and start. And whenever you get into a section which would pause, you simply get kicked out of it for a while. So that's where it's going. 2 million here, 2 million sockets open, and both on the server and the client. So what do I think about it? I think that at the moment, if I had to bet my company on it, I would definitely go for reactive or Kotlin coroutines, because the Project Loom just isn't quite there yet. There are a few things which I haven't figured out yet, which I still have to figure out. But once I've figured out, like if I could, I don't know, maybe deliver my system in a year's time or so, then I would probably go for Project Loom, because that looks very promising. Any other questions? Well, I'm going to say goodbye then, if there are no more questions.